Welcome back, dear students, to this last video on the chapter data structure. And today we are looking at the different past questions, both GC and regional mock questions, to conclude the chapter. And at the end of this video, you are going to get the link to an online quiz on the chapter data structures. Okay, without wasting time, let us proceed. June 2013, question 5, sub 1 and sub 2. As you can see, we have our question on data structure, the chapter we are just for concluding, and we have one on recursive functions, which was treated under algorithms. The link to the playlist of the chapter algorithms will be given in the description of this video. Solution. The A part says, consider the following arithmetic operation P written in postfix, as you can see. Convert P into the equivalent infix notation. So now, to ease solution, let us proceed with the sliding method. And the sliding method says that we start with the leftmost sign and we operate with the next two, with the rightmost two operands we are having. So what do we have? Sorry, not the hindmost, the leftmost operand to the sign. Sorry. So in this case, I will start with negative with the minus sign, and I'm going to operate it on 7 and 3. So as you can see, the first sign we are using is the leftmost sign. I will apply it to the next two, to the leftmost operands we are having. So I have 7 minus 3, which gives me, as you can see, the next sign is positive. So I'm applying positive on 12 and the result of 7 minus 3. Remember that we are converting an infix, we are not evaluating. That is why instead of 4, I am just having 7 minus 3 in bracket. Because if it was evaluation, I will simply have 4. But here we are converting to infix. So after adding, I'm going to have 12 plus 7 in brackets, 12 plus in bracket 7 minus 3. This is what we have. Next, then the sign now is plus, which goes with these two numbers. That's why you see them in blue. So when you operate these three, you're going to have 1 plus 5. After having 1 plus 5 now, I have my multiplication, which is going to be operated on 2 and the result of 1 plus 5, which is what we get. Then I have the addition sign, which will be operated on this and this, giving the infix expression of P to be in bracket 12 plus in bracket 7 minus 3 plus in bracket 2 times in bracket 1 plus 5. The B part says give the result of computing P. Simple algebra. I'm simply going to have 12 plus 4, 2 times 6, then 16, 12, and I add the result. You have 28, dear students. So that is the solution for the sub 1 part. The sub 2 says, let A and B denote positive integers. Suppose a function cure is defined recursively as follows. We have cure of AB, as you can see, is 0 if A is less than B, and cure of AB, of A minus B, comma, B in order plus 1, if B is less than or equals to A. A part says find the value of cure 2, 3 and cure 14, 3, showing the intermediate steps in your answer. 6 marks. So what do we have? Cure of 2, 3. We see that A is 2 and B is 3. And since 2 is less than 3, as the base case stipulates, I'm going to have 0. So cure of 2, 3 is equal to 0. Now, dear students, can you give in the comment section why the first part is our base case? Give the solution in the comment section. Now, cure of 14, 3. We see that A is 14, B is 3, and it satisfies the second condition because 3 is less than 14. So, cure of 14, 3 will be cure of 11 because I have A minus B. 14 minus 3 is 11. 3, all that plus 1. So, when A is above B, A becomes A minus B, and then 1 add to the result. So, this is the same thing. I'm going to have cure of what? 11 minus 3, 8, 3. As you can see, this one, this is it. This result gives us this plus the intermediate one. Same thing, A is still above, so I'm going to have cure of 8 minus 3, which is 5, 3 plus 1, then these two ones. This is what we have. 5 is still above 3, so this will give me cure of 2, 3, all that plus 1, and these three ones. That's why you see the ones are having different color for you to see that the one from the previous operation is still maintained and the new is coming when A changes to A minus B as the recursive case stipulates. Now, cure of 2, 3, as we saw, is 0 because A is less than B. So, cure of 14, 3 will be 0 plus 1 plus 1 plus 1 plus 1, which is simple algebra. Hence, cure of 14, 3 is 4. The B part says, what does this function do? Remember, when we're doing recursive function, in order for you to easily determine what a recursive function does, is to take the input and from the answer after evaluation, you ask some basic computation problems like addition, subtraction, factorial, power, everything, and see which one goes. When I have 2 and 3, which operation can I perform to have with 2 and 3 to have 0? Which operation can I perform with 14 and 3 to have 4? It cannot be addition, it cannot be subtraction, it cannot be multiplication, it cannot be division. But when we look keenly, we see that 2 divided by 3 is 0, remainder 2. And 14 divided by 3 is 4, remainder 2. And we see here that we are instead having the quotient from the division of A by B. That is why the function calculates the quotient of the equation A divided by B. That is what we have. So it does not return the result of A divided by B, but it returns the quotient. Okay. Next question. GC June 2024, question 6 sub 3 and sub 4. Sub 3 says, consider the three below and answer the questions that follow. Taking into account the node contents and their placement, how is this type of tree called? This tree is called a binary search tree because we see here that our node, which is 6, all the values before 6 are all less than 6, and all the values after 6 is above 6. Same thing for 4, which is in the root of 1, which is the node, the parent node of 1 and 5. The node before 4 is less than, and the node after 4 is above. Same thing for 9. So, this is a binary search tree. B. What type of tree traversal must be used if we must output the tree nodes in ascending or descending order? Explain how it will be done. Dear students, can you remind us when we have a binary search tree, which particular tree traversal gives us the node in a particular order? If you say the in order, then you are right. The in order traversal, we traverse the left subtree, then we visit the root, and finally we traverse the right subtree. This will generate the nodes in ascending order. In case of descending order, after performing the in order traversal, we read the node from right to left. Or a student could say, in case of descending order, we traverse from right to left. It is still correct. Sub 4 says, draw the binary tree that corresponds to the expression A times B minus C divided by D, which is what we call an expression tree. And remember, even to draw an expression tree, we need to follow the operator precedence. So what do we have here? The first operation we perform is A star times B. Remember that for an expression tree, the operands are leaves while the operator is a parent node. So for A star B, A and B will be the leaves while star will be their parent. After multiplication, the next operation I will perform is division. So C and D will be leaves and their parent node will be division. After having these two subtrees now, I'm going to link them with subtraction. And that is how our expression tree resembles A times B, then C divided by D, and they are linked with a minus sign. As you can see, write out the tree if it is output breadth first. Output breadth first, this is what we have. So here we are reading from left to right and here from right to left. So from left to right I have times, I have subtraction times division, A, B, C, D. But it is from right to left, I have minus, division, multiplication, D, C, B, A. That's the answer to June 2024 question 6 sub 3 and sub 4, which came for 9 marks, dear students. We proceed to the next question. Remember to like, subscribe, and to share the video in order for our community to grow massively. Thank you very much. Center Regional Mock March 2024, question 601 and sub 2. The first part says, differentiate between the following pairs of items, giving an example in each case. Static data structure has a fixed size at compile time, e.g. array, while dynamic data structure is one whose size can change dynamically at runtime. And we mean change dynamically means that it can be increased as well as it can be decreased. And an example is a linked list. And this is the major difference between a static data structure and a dynamic data structure. Composite data type and non-composite data type. A composite data type is a data type composed of atomic and or other composite data type. An example is records, while a non-composite data type is one from which composite data types are created, e.g. integer. That's the difference between a composite and a non-composite data type. Sub 2. A binary search tree is an example of a data structure, correct? Insert the following names in the binary search tree in the order they are given: John, Sonia, Agatha, Williams, Ben, Paul, Tonya. So this is what I'm going to have as my binary search tree. Let me explain. Remember, when we are drawing a binary search tree, our first element is our root, as you can see. So John is our root. From there, Sonia, we compare the first character. S is above J. That is why Sonia comes to the right, because for a binary search tree, the values above the root goes to the right, while those below the root goes to the left. So I have Sonia. Then Agatha. Agatha A is less than J. That's why Agatha comes to the left. Then I have W. I compare with the root. W is above J, so we come here. Sonia is already there. W is still above S because I compare also with the note I'm seeing. W is above S, so William comes to the right of Sonia. Then I have Ben. Ben, B is below J, so he comes here. We compare with Agatha. B is above A, so Ben comes to the right of Agatha. Then we have Paul. P is above J. When you come here, P is below S, so Paul comes to the left of Sonia. Then Tonya, T is above J. When we come here, T is above S. When we come with W, T is below W, so T comes to the left of William. And that is how our binary search tree with the nodes provided is created. The B part says, explain how you will determine if the name Tonya is in the binary search tree. How will you determine? First of all, we are going to compare Tonya with our root, which is John. We see that there is no match between the root and the element we are searching for. So, Tonya will be compared with the values to the right of John, since T is above J. T will be compared to S since there is no match and T is above S. T will be compared with the values to the right of Sonia. T, Tonya will be compared with William, and since there is no match, T will be compared with the left values to William since T is less than W. And finally, we shall see that there is a match between the left node of William which match with the value we are searching for. Remember that this is the same thing as performing searching in a binary in a sorted array, binary search, hence the name binary search tree. For those of you who still have problems when it comes to searching and sorting algorithms, I will advise you to visit the playlist on algorithms with the link provided in the description. Now, the C part says, state the result of the pre-order and post-order traversal of the above tree. So, I'm going to use this our funny method to obtain the pre-order and the post-order. So, for the pre-order, where are the mark placed? They are placed to the left of each node. So, when I traverse, I have John, Agatha, Ben, Sonia, Paul, William, Tonya. That's what we have for the pre-order. As you can see, John, Agatha, Ben, Sonia, Paul, William, Tonya. Now, for the post order, it is to the right, as you can see. So when I move, I have Ben, first of all, Agatha, Paul, Tonya, William, Sonia, and finally John. And that's how we obtain the post order traversal, dear students. So that is what was expected from students in the Central Regional Mock 2024, question 6 sub 1 and sub 2, which came for 11 marks. The next question, GC June 2013, question 4. It is true, this question, remember, bring us back to some concept when it comes to mathematics, combinatorics. It says, it is a full question. Suppose that the vehicle registration numbers in Cameroon have 4 letters. Problem battery low. The first two letters represent a region of Cameroon and the last two represent a registration series. The four digits represent a number in a series. However, the four digits cannot all be zero. There are 10 regions in Cameroon and a series is any two letters of the English alphabet. For example, NW 1024AZ 1024 is a number in the AZ series for the Northwest region of Cameroon. However, NW0000AZ is not a valid registration number. Yes, because they said the four digits cannot all be zero. That's why this is not valid. How many cars can be registered within a given region for each series? That is, for a particular region and for a particular series, how many cars do I have? Can I have? For each region, we have a series of four digits. The selection of a digit, let us say just among the 10 possible digits, because from 0 to 9, you have 10 possible digits. And the number of ways I can select one digit out of 10 is calculated as 10 combination 1, which is equal to 10. That's for the A part, which is incomplete. Hence, for four digits, we will have 10 times 10 times 10 times 10. This is because this is for the first digit, the second, the third, and the fourth. So to have those four digits, I will have 10,000 ways. But remember, it was said that 000 is not possible because I can have 0 as the first number, the second, the third, and the fourth. Meaning that the series 000 is not possible. We will have a total of 10,000 minus 1, which is 9,999 cars. So for each series in each region, there is a possibility of having 9,999 cars. The B part, the total number of series. In a particular region, a series comprises of two letters of the alphabet. And since you have 26 letters in the alphabet, I think so, the number of ways of selecting the first letter is 26 combination 1. The second one is 26 combination 1, 2. So I have 26 times 26, giving me a total of 676 series. So per region, I can have 676 series. Now you might ask yourself, why combination? From combinatorics, the number of ways you are selecting an item from n elements result to n combination. The total number of item combination 1. If I'm selecting one item out of a list of items, provided there is no further constraint. The C part says, calculate the total number of cars that can be registered in Cameroon. So now, per region per series, I can have this number of cars. Per region, I can have this number of series. It means that for a particular region, I can have this times this possible number of cars. So for Cameroon in general, I will have this times 10. In any region, we can register 676 times 9,999, which gives us 6,759,324 cars. I hope I could have this number of subscribers in some months to come. So, number of cars that can be registered in Cameroon will be given by 67,593,240 cars. Sub 2. Find the minimum number of bits to represent the number section of vehicle registration number. The number section is treated as an integer. Remember, from the first lesson, we saw the different sizes of an integer. The minimum number of bits required for a number section is 4 bytes. And since a byte is equal to 8 bits, so the minimum number of bits is 32 bits. B says, using your answer in A and given that a character is represented using 8 bits, find the minimum number of bytes that will be used to represent a complete vehicle registration number. And now that here they are talking about bytes. What do I have? Minimum number of bits is equal to minimum of bits for number section plus bits for letter section. So what do I have? For a number section, I have 32 bits. And for the letter section, since I'm having 4 different letters and the question says, a character is represented as 8 bits. So I have 4 times 8. This is 32 plus 30. That gives us 64 bits, which gives us 64 divided by 8 bytes. So the minimum number of bytes to use when representing a registration number is 8 bytes. Sub 3. Which will you advise the Ministry of Transport of Cameroon to use? An array or a linked list as a data structure of vehicle registration? Justify your choice. In this case, Dear student, which one will you propose? And obviously it is a linked list. Why? Because linked lists are dynamic data structure which can grow and be pruned, that is, it can be reduced in size. Thus, no need in defining a limit size for a linked list. Also, a vehicle can be easily added and deleted from the set, which is perfectly correct. A programmer who goes and use an array with this particular number of a size, because this is the maximum we can have, in case we do not have up to this number of vehicles, it means that a lot of memory space is going to be wasted. And if in the nearest future a different methodology is applied which conclude to an increase in the number of cars, then an increase which leads to more cars as this number stipulates, then we will need another array, or we need to discard the array we are having for an array of a bigger size which is consuming resources. That is why a linked list is easily used, is the best choice, because the size can be increased and reduced since it's dynamic, and also insertion and deletion is easy. Next question, the Bamenda mock 2024 question 6. To be sincere with you, dear students, once I saw this question, I was very astonished, and I personally, in my heart, congratulated the team who set this question, because this question it is special. I love this question. The question says, why do I love this question? Because it is made up of a lot of reasoning, not complicated reasoning, but simple reasoning. It says an electronic voting system functions as follows. Voters can enter their voter ID into the system online. ID comprised of name and ends with 2 digits for age. The ID is pushed onto a stack. If the age digit is less than 20, the ID is popped off the stack and a new ID enter. If the age digit is greater than 20, then a new ID is entered. A counter, so remember here that if the age is greater than 20, then it is saved. Then we look for another one. A counter, in fact a total, keeps track of the total number of voters so far registered. A code has been implemented to automate the process as follows. So this is just for those who do not understand this particular description, because here it's just the algorithm given in step form, whereas here it is in pseudocode. So to cut it short, once a particular ID, a voter ID is entered, we compare the digit using the method isDigit. For those who do not understand the description above, we compare the digit. If it is not above 20, or if it is less than 20, then it is not saved. Whereas if it is from 20 upward, then it is saved inside the system. The A part says, what is the name given to an algorithm such as the one above? Justify for 3 marks. Remember that this is a full question, a full 17-mark question. Solution. It is a recursive algorithm since it calls itself at line 8 and 11. Remember, this is the algorithm valid, as you can see. So here, we are calling valid, and here we are still calling valid. And now you will say, we are not sure that this is the method, because look at line 3, we say this is the function valid. And inside valid, I have instances of valid again, which shows that it is a recursive function. And also, we call ourselves after condition 6 is true, we call at line 8. And if condition 9 is true, we call again at line 11. Otherwise, we exit. So this is a recursive function since it calls itself at line 8 and 11. The B part says, explain briefly how a stack is used when a function is executed. When the function is executed, a stack frame is created. The value for local variables and parameters are stored in a stack frame, as well as the return address or the return pointer of the caller function. Each time a recursive call is made, a new stack frame is created and the same information is stored. Once the function completes its execution, the flow of the program is returned to the instruction just after the function called. And this was just explained. Remember, when we treated subroutines, we had a full lesson about stack frame and how its content changes when a program containing a subroutine is executed. And that is what we are asked in this question B. Now, top 2. The following voters registered with ID in the order, that's the order we gave. Only 5 voters are needed, meaning that what? Once our size, the size of the stack we are using is 5 is full, we stop. By applying the functioning principle of the voting system and the algorithm provided, show the state of the stack S each time a voter ID is entered. At the end of the stack, at the end, the stack is expected to have exactly 5 voters ID. The state of the stack after entering the first two IDs as follows. So when I enter Anna, remember that if the last two digits are not up to 20, then we don't insert, we move to the next. That's why upon adding Anna, the stack remains empty because 19 is below 20, so we don't insert. And Abba 21. 21 is above 20. That's why it is inserted. I hope you're understanding. So if the last two digits is below 20, you are not inserted in the stack. Whereas if it is above 20, that is when you get inserted into the stack. That is what we have. Now, let us proceed. For the sub to this, what we have, initially our stack is empty. Upon adding ANA 19, it remains empty like it was given in the description in the question. Upon adding ABBA 21, that's when it is added because 21 is above 20. So now the next one is Paul 19. So upon adding Paul and 19, will this remain empty or filled? Because here is still ABBA 21. Will this be empty or filled? Correct if you say empty because 19 is below 20. So upon adding Paul, that will be my content of the stack. The next name is Peter 20. This is what we have. Upon adding Peter 20, my stack is going to be what? About 21 and Peter 20 because 20 is not less than 20. It is equal. And the question here says, if the age is less than 20, the ID is popped off. That's what we have. And I understand here that you say if the age is greater than instead of greater than or equals to. But when you come here, the question here says if I digit is less than 20, we pop. Else, if ID is greater than or equals to. So you see that the step form and the pseudocode give more clarification. That is why Peter 20 is added because here I digit should be greater than or equals to. In case it was just greater than, then even Peter will not be added. But fortunately, they say greater than or equals to. So upon adding Peter 20, this will be the content of my stack. From Peter 20, I go to John 18. 18 is below 20, so the stack remains the same. Mary 19, upon adding Mary 19, 19 is below 20, the stack remains the same. Kelly 30, upon adding Kelly 30, 30 is greater than or equal is above 20, so Kelly will be added as the third item in the stack, as you can see, dear students. The next one is Joe 23. Upon adding Joe 23, 23 is above 20, so Joe 23 will be the fourth element that will be the content of my stack. Billy 17, upon adding Billy 17, 17 is below 20, so my stack remains the same. Then James 25, upon adding James 25, 25 is above 20, so my stack is going to be as you are seeing. Now, I'm not going to compare for Jill 22 or Steph 20. Why? Because in the question they said the stack is expected to have exactly 5 voters, and I have 1, 2, 3, 4, 5 voters exactly. So the algorithm will not stop, but this is how the content of the array will be upon adding Jill 22 and Jill 20 because the condition says here that for us to add, the ID should be greater than or equal to 20 and my total should be below 5. Dear students, that's what they said. So we are okay with the content of the stack. Sub 3. In order to enhance easy search of voters from the database, a binary search tree is constructed by popping IDs out of the stack. The first ID pop is the root. Now, dear students, that's why I love this question because it goes across most of the different sections we saw under this chapter, subroutines, as well as some different notions of algorithms. Now, this is our stack. When I will pop a value out of the stack, dear student, which value is going to be popped out? Is it Abba, Peter, Kelly, Joe, or James? If you said Abba, then you are wrong. Whereas if you said James, then you are correct. Why? Because a stack follows a LIFO principle. The last element to be added is the first to be popped out. And the last element that was added is James 25. So to consult our tree, our first element, which is James 25, will be our root. That is what we have. So James is our root. From there, the next item is Joe. When you compare J and J, they are the same. We move to the second letters. O is above A, so Joe comes at the right of James. K, when you compare K and J, K is above J. When you compare K with this J of Joe now, K is still above, so that's why Kelly is at the right of Joe. Then Peter, P is above J, above J, above K. That's why Peter is to the right of Kelly. Finally, Abba, A is below J. That's why Abba is to the left of James. So this is our binary search tree where we draw from the content of the stack by popping values. Remember that the student who started by Abba is considering the stack to follow a FIFO principle, which is wrong. The B part says, write down the IDs in the correct order when the tree 1 in subtree A above is traversed post order. As you can see, I've already indicated the beginning and the start. Now what we have for post order, the mark is placed to the right, dear students. So if I want to do the post order of this tree, I'm going to have Abba, Peter, Kelly, Joe, James. So the post order traversal is that Abba, Peter, Kelly, Joe, James. And the C part says state the big O time complexity when the ID James is searched. If I want to search James 25, it will be the first comparison. And when you compare items in a list and the item you're searching for is the first, what's the time complexity? The time complexity will be big O of 1, constant time complexity. That's what we have, dear students. Nice question by Madam Assistant Mock 2024. Next question. Northwest Regional Mock March 2024 question 7 sub 3 and 8 sub 4. Design a suitable hashing function such that the result of the hashing function should be such that every index of the array can be addressed directly. The simplest hashing function gives us addresses between 0 and n. For illustrative purpose, n to be 9. That's what we have. Meaning that the hashing function gives us addresses between 0 and 9. And if I have 0 and 9, we know that the most popular hashing function is the modulus. And if it's from 0 to 9, from 0 to 9 gives us a possibility of 10 cells, meaning that my hash function is going to be h of key is equal to key mode 10, because from 0 to 9 I have 10 indices, and the modulo number always corresponds to the number to the index number. B. Using a trace table demonstrates how you could store records with the following customer IDs, as you can see. So here, this, as you can see, yes, n is 9. So here they say address is equal to key mode n plus 1. So key mode 10, as I gave. So the B part, let us see how we are going to add. That's my array index. I have my customer ID. Now, remember that when you're taking a number, as it was explained under hash table, when you take a number mode 10, the result is simply the unit value, as you know, dear students. So for this first one, this number mode 10 will return 6. This is where it's going to be stored. This mode 10 will give us 0. That's where it's going to be stored. This will return 2. That's where it's going to be stored. This will return 6. And this is where it's going to be stored. Do not ask me why I'm storing it here, because in this question, no method of handling collision was given, and we were not asked to handle collision. They just said, use a trace table to demonstrate how you could store records in the following customer ID. That's why from the index I have, I store the element at that position. So this will return 7. That's where it's going to be stored. And the number are all okay. Like there is no number to be computed again, so the other cells are empty. So this will be the content of my table after performing this particular block of code for this different customer ID. The C part says, is there any problem encountered in inserting the keys? Justify your answer. Yes, there's a problem, which is collision, which occurs when inserting the key 64636, since its index is occupied by the key 45876. That's the problem we encounter when inserting the keys, dear students. And I hope, and I think, and I'm sure that you know how the format, or the view of the hash table will be if we were handling collision either using open addressing or closed addressing. because it was done under hash table, and exercise was done to make sure you carefully understand the concept. The next question, evaluate the following arithmetic operation. As you can see, we are using sliding plus with 10 and 5. So 10 plus 5, 15. So we are now having 3, 15 star, and we apply star with 15 times 3 gives us 45. That's the answer for the first part. The second part, remember that we focus on the leftmost sign. In this case, it is multiplication, and it goes with the two digits that are to its left, which are 9 and 3 in this case. 9 minus 3 gives us 6. So I'm supposed to have 987. All these three gives us 6. Then star plus minus. That's what we have. The next one now is star. The next two digits, 7 and 6. 7 times 6 is 42. So I'm supposed to have 9, 8. This 3 gives us 42. Then plus minus. Then I have plus. When you go with these two, this 3 gives us 50. So I'm supposed to have 950 minus. Now we have, and now when you operate this, 9 minus 50 is negative 41. That's for the B part. The C part, plus with 1 and 2. When I add, I have 3. So I'm supposed to have 5, 3, 4, star, plus 3 minus, which is what we have. The next one is star with 3 and 4. When you multiply, you get 12. Next sign now is plus with 5 and 12. And when you add, you have 17. Then when you take 17 minus 3, it gives you 14. That's what we have for this 8 sub 4 of the Northwest Regional Mock 2024. South Regional Mock March 2024, question 5 sub 1. The reverse Polish notation RPN of an arithmetic expression is as follows. As you can see, a stack S is used to evaluate the expression following the algorithm below. Algorithm to evaluate RPN. Yes, as you can see, this is not the algorithm that was described when we were seeing how to evaluate RPN using a stack. So I'm not going to read all those steps. A. Use the algorithm step by step to evaluate RPN expression. Show the state of the stack at each step. I'm sure that this is just a simple problem for you, dear students. So the stack during evaluation at the end is what we are going to have. So the first thing, we know that if it's an operand, we push in the stack. And once we have an operator, we pop out the values, we evaluate them, and we push back the result. So I'm going to push 9. As you can see, when I add 9, I add 2, I add 3. Now, as I have multiplication, I pop out two values which are 3, 2 and 3. I evaluate them. As you can see, 2 times 3 is 6. I push back the result. So when I remove these two, 9 is the only element. The result is 6. I push it back. That's why I told you that when you are removing two elements, in the next cell, you need to show the operation under and the result above. From there, we add 4. I have one subtraction, 6 minus 4, 2. I have another subtraction, 9 minus 2, 7. I add 8, I add 2, I add 3, I add 4. Then I have multiplication. When I multiply this, I have 12. Addition, when I add these two, 14. Subtraction, when I take 8 minus 14, negative 6. Remember that it's always the one below minus the one above, not the reverse. Then I have addition, 7 plus negative 6 is 1. So this is the content of the stack during the evaluation of the RPN using the algorithm provided. The B part says, give the equivalent binary tree representation of the expression. So dear student, here you just need to be very observant because it is just like in the sliding method. Or you can base yourself to the different operation we have been performing, but from the start, it will be a little bit difficult for you to view it. So here, what do you see? I will first of all have 2 and 3 as the leaves, then we star as their parent node because this is the first evaluation I'm doing. From there, the result of this has as parent negative, then it goes with 4 and so on. So this is the tree we are going to have. So 2 times 3, as you can see, first of all, this is there. From there, the next operation is subtraction, and subtraction goes with this result and 4. That's what we have. From there, I have subtraction again, which goes with all what I've evaluated from here with 9, as you can see. After I'm done with this, I have all these series now. First of all is multiplication with 3 and 4, as you can see, dear students. Then I have addition with 2 and this result. This is it. Then I have subtraction, which result to this. Then I have addition, which links down the two different subtree. So this is the equivalent binary tree, the expression tree for the RPN given. C. Which well-known tree traverse algorithm is suitable to evaluate the expression from the tree representation in question B above? Justify your answer. Post-order traversal as it processes operators after their operands. That's what we have. Next question. The Southwest Regional Mock 2023 question 8. If another full question. Consider the binary tree in figure 2. That's what we have. What is a complete binary tree? Is a tree above complete? We know that a complete binary tree is a binary tree in which each level, except possibly the last, is completely filled and all nodes are as left as possible, as you can see. The first level, 1, okay. Second level, level 0, 1, correct. Level 1, 2, okay. Level 2 is supposed to have 4, but it has 3. So it's that the last level is incomplete, so it is okay because all the other levels are complete, but they say the node should be as to the left as possible. So this will be a complete binary tree if Q was the left child of O. So this tree is not a complete binary tree. I will allow you to give the type, the name that corresponds to the type of tree in the comment section, dear students. B. State in what order node, whether a node, its left child and its right child will be visited in each of pre-order and post-order. Hence, determine the pre-order and the post-order traversal of the tree. Pre-order, remember the matrix, just that root is replaced with node. So I have node left, right, post-order, left, right, node. The pre-order traversal, as you know, the left, the root first of all, so L, E, C, then J, O, Q. This is a simple binary tree. This is a simple BST, so performing the traversal here won't be difficult as compared to the ones we had in our example and the different exercises. C. Node L is to be deleted from the tree above. Draw the resulting binary tree when the replacement node is chosen from the left subtree. So here they precise. They say L is removed. What are we going to have if we are taking the replacement from the left subtree? Remember that L has two children. And when we are deleting a node having two children, there are two possibilities, but here they precise that it should be taken from the left subtree. And remember that if you are taking the replacement node from the left subtree, then it should be the highest of them, whereas if it is from the highest subtree, it's the lowest of them. So since they say from the left subtree, this is the left subtree of L, and which one is the highest here? It is G. So I'm going to have G replacing L, and that is how the tree is going to be. Now we have. So I will simply have G, E, C, then O, Q. D, give an array representation for the binary tree in figure, supposed to be figure 2. Now we have L, E, O, C, G. Since there was supposed to be a node here, it is not. So that cell remains empty. Then I have Q. That's the answer, dear students. Top 2. Suppose you have three stacks S1, S2, S3 with starting configuration shown on the left of figure 3, where stack S1 contains the letter A, B, C, D, and finishing configuration shown on the high where the letters have been moved into stack S3. Give a sequence of push and pop operation which move the letters A, B, C, and D from S1 to S3 as shown below. For example, to pop the top element of S1 and push it into S2, you will write S2.push into S1.pop. Or you can simply say X is equals to pop. That is, first of all, remove. That way you say X is equals to S1.pop. Then you now push that X into S2. So if I want to remove A and put it in S2, I can either use an intermediary value X, which takes the value I am popping from S1. Then I take that value now and I push it in S2. Or using this expression, what you are pushing in S2 is directly what you are removing. It remains the same. It's just like you are just replacing X. It's the same thing. So notation 1, notation 2. If I want A, B, C, and D to enter S3 in the format A, B, D, C, what will I do? I cannot remove A and I put that at the top. Remember that it's a stack, and when you're adding, it goes directly at the bottom. So what do we have? I first of all remove A and put in S2. That's what we have. So I first of all remove from S1, then I push in S2. Either use notation 1 or use notation 2. And this is what you are going to have. I am removing A and I'm putting in S1, in S2, sorry. From there now, because remember in S3, the first element I must have in S3 should be C. And for me to obtain C, I must first of all remove A and B, which are above, because a stack removal is done from the top. Now my top here is B. I remove again and I push in S2. That is, I remove the top element from S1. I push it in S2. This is what I'm going to have. Now my top element is C, so I can remove C and put it directly in S3. So this is what I'm going to have. So I remove the element at the top of S1, then I push it in S3, not more in S2, because it's the element that should be at the bottom. That's what we have. This is what it gives. Then I remove D. Since D, the next element should be above D. I remove D from S1 and I push it directly in S3. That's what I'm going to have. From there now, I remove B and I put it directly here, as you can see, because B is the next element. So I remove the element from the top of S2 and I push it in S3. That's what we have. So that's what it gives. And finally, I remove the element from the top of S2 now and I push it in S3. That's notation. And that is what we have, dear students. So for the element to move from A, B, C, and D to enter S3 in the order given in the question, these are the series of operations to be done, whether you're using notation 1 or notation 2. Okay, dear students, I think we are coming to the end of this video. We have gone through a lot. We saw all the different data structure, the type that we could see. We saw the applications, where they are useful. And today, we solved some questions in order to give more understanding to the chapter. I hope you enjoyed this last video. Do not forget to like, to subscribe, and to share the video in order to increase our community. And why not drop in a comment which will serve as a feedback for us. And remember, in the description of this video, you have the playlist, you have the link to the playlist on algorithms, because you saw that this chapter is related to algorithms. And for those of you who never watched the videos on algorithm, the link to the playlist is given in the description. And also, you have the link to the online quiz on the chapter data structure, as the tradition of our channel stipulates. Because after going through all of this, first of all, after this video, you have questions that will follow, which will be required to answer. The question will be equally given in the WhatsApp channel, and the solution will be given in the weekend, and also the link to the online quiz, which is already guided. So after solving the question, you will have your answer and the solution. Thank you very much, and see you for the next lesson.